Alrighty, ladies and gentlemen, so right now we're going to have a review on the intermolecular and intramolecular forces present when we're talking about bonding. When we're dealing with bonding, you're looking at it from two different perspectives. You're looking at it from two different perspectives, this intramolecular force and intermolecular forces. Intramolecular forces with the prefix intra, that means within. So you're looking within the molecule or within the compound. That's within the bond itself. Intramolecular forces are talking about these bonds present when you make them. Intermolecular forces are talking about between atoms. Between the atoms. Intramolecular forces, we're going to narrow the field a little bit, zoom. Intramolecular forces are things like make bonds directly. You're looking at the bonds directly. They're way strong, they're highly attractive forces, much like these ionic compounds here, when we're talking about sodium and chlorine making that ionic bond salt. This donation of this electron makes an ionic bond, which makes it very, very, very strong and hard to overcome. But also covalent structures deal with this intramolecular force, and we can use it to our advantage to see the stability of an atom. And we're going to use what we know about Lewis structures here to make carbon tetrachloride. So I see 4 bonding spots available, and I see 1 bonding spot available. So my best problem-solving skills say that carbon's probably going to go in the middle with all these chlorines just dancing around all the free spots. And now I'm going to do some manipulations here to move it around. And we know, maybe, here we go. And we know that with 4 things around it, I'm going to flip that one all the way upside down, bow. And where my green and red dots overlap, that creates a bond. And with 4 things around it, this carbon tetrachloride actually has a special shape name we call tetrahedral that we draw with proper bond angles, because we know all of these electrons right here would not want to be this close to each other. Because what do like charges do? Like charges repel each other. So what they do is, because this is a covalent structure, and sharing is caring, and if I care, I take shape, my covalent structure, they move as far away as humanly possible while staying in this bond. All right? And if they're far away from each other, they're more happy, more stable, and we still get this sharing all the way around the molecule. All of these electrons are shared amongst all 4 of the, or 5 of the compounds involved, I should say. Makes a nice little cloud. Of course, your clouds will be better than mine, but you get the picture. They start sharing and overlapping and running around, all around and in between, making our carbon tetrachloride. All right? And the sharing is what we know about covalent structures, and this donation is what we know about ionic structures. So, and over here, we have things about intermolecular forces. Intermolecular forces is that in-between idea, what happens with the neighboring molecule, and how tightly they get held together. Intramolecular forces are most prevalent in covalent bonding things. So remember, the first thing to do when you're comparing bonding natures and bonding forces is this inter versus intramolecular forces. Is it ionic? Is it covalent? Is it ionic or is it covalent? When comparing the two, intramolecular forces are weaker than intramolecular forces are stronger than intermolecular forces. What's happening within an atom is always going to be stronger than what's happening between atoms, okay? So intra is stronger. But when we're dealing with intermolecular forces, we're still addressing this in between. What happens when one water molecule is right next to the next water molecule? So it's happening between this one and this one, and how attractive they are in the spaces between. What keeps them together is water's natural polarity. We know that water is polar. Water is polar. And this dynamic we have here with this partial positive and partial negatives that I'm drawing, partial positive and partial negatives, mean that they're electrostatically attracted to each other very, very intensely. And how attractive they are to each other is how we get states. These different states are all about how attracted you are to your neighbor. When we're talking about a solid state, my atoms are very, very tightly packed together. They don't move out of place, and they just buzz around and hang out in place. But as I increase in energy here, as I go up in energy, I get more space. I start to separate. My attraction to my neighbor is lessened as I move up in energy, and then I get something that looks more like a liquid. If I continue to increase in energy, I move to a gas. I move into my gaseous phase where things have lots of energy and are moving around almost constantly and never in one place for very long. So when we talk about these state changes, when we go from a solid to a liquid, that's called melting. And as we go from a liquid to a gas with some additional heat, that's called vaporizing. And the reverse is true too. We have to deal with the particle spaces as we condense and as we freeze, putting energy into the system, my system being whatever situation I'm dealing with, putting energy in or taking energy out, giving the particles the freedom to stretch and move. So if I have this extra heat energy, my water molecule here has the ability to stretch and move and become further and further away. So as I increase from solid liquid to a gas, going up my energy scale, my attraction is stretched to the max. I no longer am as attracted with this water molecule to this one. Capiche? This distance is way increased compared to this distance. So this side is becoming more liquid. All right? That side's becoming more liquid. And these relative attractions are how we get these state changes. And we can address solid, liquid, and gases based on how many intermolecular forces are involved. There's 3 different flavors of intermolecular forces here. We have London dispersion forces, dipole-dipole moments, and hydrogen bonds, all of which play a key role because they act cumulatively. They are a cumulative effect here. So it's a layered approach, kind of, sort of. So you're thinking about London dispersion forces, but if it's polar, you also have a dipole-dipole moment. Or if it's a specific dipole-dipole moment with certain atoms, you have London dispersion forces, dipole-dipole, and hydrogen bonding, okay? It's a cumulative effect. All of these things happen at the same time on certain atoms. So it's an all for one and one for all type situation here. So let's break it down one piece at a time. The London dispersion forces are London dispersion forces here. That is when we're starting to deal with the polar things. London dispersion forces are polar. That's when you have any 2 polar molecules. And remember, polar means unequal sharing. We can see an example of polar when we're talking about water. Water has that polarity to it where it has a slight positive and slight negative to it. And this polar side of water just means that the electrons are attracted to this electronegative oxygen up here. So what they want to do is they want to move towards it. They still hang out down here around my hydrogen sometimes, but a majority of the time they're up here on oxygen. That's why it has that red hue to it. So it's not that they don't go to the hydrogens, they just spend more of their time up here with this oxygen. Oxygen's greedy, it's highly electronegative. It's highly electronegative. Because it's up there pretty close to fluorine. And remember, as we go up diagonal close to fluorine, we're talking about an increase in electronegativity. So in regards to your periodic table, let me make a makeshift periodic table here. All right, fluorine's somewhere over here, right? So fluorine's over there. As I continue to move up my periodic table here, anything right close to fluorine is highly electronegative, okay? They're highly electronegative. And having this electronegativity or this polar idea gives you dipole-dipole interactions, or dipole-dipole interactions is how I remember it. And it holds the molecule together. But it's not so much a tight hold like a bond is. It's more like an intense attraction. It's an intense attraction. Even strong relationships get tried every once in a while. So if you add some stress, some heat stress, or energy stress to a dipole-dipole moment, you can separate it. And I have this dipole-dipole moment here because we know this sulfur has these two lone pairs, and it pulls more of the electrons towards itself up here, giving it that polar side. And we know sulfur is a part of 6A, and 6A has a special polarity side to it, right? So they pull it up here. And if I have these two polar molecules next to each other, this intermolecular force right here is a dipole-dipole attraction. This positive side of this hydrogen is really attracted to this negative sulfur right here. It's really tightly attracted. But if I add some heat or I add some energy, giving it the freedom to move about, I'm going to lessen that attraction and separate. I'm going to separate. Or if I take away that heat energy, I kind of start to come back because this negative right here up top is really attracted to this positive right here. So it's going to slide back. In the absence of the energy or in absence of the stress to move, we're not going to move. We're going to follow those attractions. Okay, so this is between two polar molecules. So you got to learn how to distinguish if they're polar, if things are polar. So this is where that molecular geometry comes into effect, when we can see the dispersion of electrons based on its shape. And as we move up in the world, so this is your mid-grade. Dipole-dipole moments are your mid of the line. These are your middle force. These are your middle forces. Your strongest force is hydrogen bonding. And I have bonds in air quotes up here on purpose. When I say hydrogen bonds, I'm not really meaning a bond like sodium chloride bonds. I'm not talking about this kind of bond up here. What I'm talking about is a really intense attraction. It's an intense attraction between a couple neighboring molecules. And hydrogen bonds are a special subset of dipole-dipole interactions because these attractions are so strong between electronegative atoms. So to have hydrogen bonding, you have to have a hydrogen, of course, plus a fluorine, oxygen, or a nitrogen, a member of FON in your adjacent molecule, okay? These are highly electronegative atoms, and they have specific polarities that make them attractive 2 electrons. It's the reason why water takes so long to boil. Water takes so long to boil because of the intense hydrogen bonding. There's air quotes right there. The intense hydrogen bonding. So let's think about it. As we're making our pasta or our oodles and noodles, we have a pot full of water molecules, right? It's a pot full of water molecules. And we know that one water molecule is pretty polar. It's very polar. So they align themselves in this positive negative orientation I have annotated here. So as we look at it, the reason it takes so long is our heat energy has to come in here, right? And separate this intense, almost magnetic attraction between this hydrogen and this oxygen. And that takes time to do. It takes time to separate that out. So eventually it does happen because enough stress and pressure, things will separate. So then take it for example, we'll take those and move them on about and move them away out of line, but it doesn't make them any easier to come back to. We know that water does boil because of life experiences. What takes it so long is that intense hydrogen bonding, holding it together, keeping it in place, resisting that change. They want to stay together because they're electrostatically attracted to each other based on this temporary dipole hydrogen moment we got going on here. So hydrogen bonding, quote unquote bonds, is a subset.
All my wonderful custodian, come on down for the celebration. All my wonderful custodian, come on down for the celebration.
So the dipole-dipole moments are a special subset here. So hydrogen bonds are a special subset of dipole-dipole interactions because dipole-dipole interactions happen because things are polar and have this magnetic attraction almost. So then this other subset, a stronger version of a dipole-dipole interaction. And it's only stronger when it has these 3 elements involved because they're highly electronegative. And once they get started, they don't like to separate right here. Capiche? So I've told you the mid-grade. I've told you the strongest. By default, we got the weakest up next. Intermolecular force, we abbreviate that IMF. And that is London dispersion forces, aka van der Waals forces. And London dispersion forces, or what we call in class LDFs, are attractive forces that exist in all covalent compounds. The special thing about IMFs, and particularly London dispersion forces, is that all covalent compounds experience this London dispersion force. So it's a layered approach. So if anything at all, you might not have hydrogen bonding and you might not have a dipole-dipole moment, but you will, ooh, there we go. You will have a London dispersion force at some degree. Might not be too intense, but it will be present. Or if you're polar, you can have dipole-dipole moments. You can also have London dispersion forces. And if you're a member of FON, you have dipole-dipole moments, hydrogen bonding, and London dispersion forces. They're a layered approach. They're cumulative. So you have to take into account different perspectives here. And with London dispersion forces, they are an attractive force that exists between all covalent compounds as a function of their number of electrons. When I say their number of electrons, I'm talking about their total number of electrons. We get the information from their atomic number, friends. Remember, way back in the day when we did Zappin', we talked about what makes a neutral atom versus an ion and how we calculate those number of electrons. The more electrons involved is the stronger the LDF. The stronger the LDF, you have more electrons, making it hold tighter together. And this attraction comes from the idea of being polarizable or polarizability. Because we know all electrons are moving, they are consistently moving around and they can shift in response to being next to someone. All right, giving a very temporary, very moment to moment to moment dipole moment where they have a hot second of being partially positive and partially negative. Kind of like what we see right here with this blob. Right now, the blob is moving to the right. for 1 split second. But if I move along, it starts to move back to the left, and then back right, and then back left. It kind of ebbs and flows depending on what it's around. So if I'm the neighboring molecule and I get real close, it'll move away. If I move away, it continues to live its best life. So we know that these electrons are in a cloud around my atom, moving and living their best electron lives, zipping and bobbing and ebbing. In these orbitals we know, but free to move in between them, right? And because they're moving at such rates and they're always present for any 1 second from time to time, you can have varying degrees of electrons on each side. So you see I have a sum right here and a whole lot right here. That just means they're moving. And then the next, moment to moment, they're different. So moment to moment, moment to moment, my electrons are in different degrees around my atom here, okay? So let's do an example. I want you to identify the substance. Let me move this out the way. I want you to identify the substance with the strongest London dispersion force, or LDFs. And how do we calculate that again? That is based off of the number of total electrons. So we got to do some inventory. Here we see a carbon and a hydrogen. How many carbons do we see? I see 2 carbons, and I see 4 hydrogens. That subscript down there tells us our number of atoms. And each carbon is contributing 6 total electrons. Each hydrogen is contributing 1 total electron. 6 times 2 is 12. 4 times 1 is 4. So I'm getting 12 electrons from carbon and 4 electrons from hydrogen. I'm going to add them all up. That's what that fancy 3 thing is. That's called sigma. It means to add up. So if I add up 12 plus 4, I get how many electrons, friends? 16 total electrons. So I got 16 total electrons in C2H4. All right, I'm asked to compare between C2H4 and C6H12O6, aka glucose. So here we go. I'm going to do the same exact process. CHO. I see 6 of them. I see 12 of them. I see another 6 of them. Each carbon is contributing 6 electrons. Each hydrogen is contributing 1 electron. Each oxygen is contributing 8 electrons. And we multiply across, giving us 36 here, giving us 12 here. 6 times 8 is 48. So I have 36 electrons from carbon, 12 electrons from hydrogen, and 48 electrons from oxygen. So all I gotta do is add up, and the things I'm adding, friends, I'm not just doing this arbitrarily. I'm adding up all 3 of those things right there. So I got 36 plus 12 plus 48. That gives me some 96. Yeah, 96 electrons. 96 electrons altogether. So comparatively, I'm looking at London dispersion forces only. So I ain't got to worry about if it's polar or non-polar yet. Who is my winner? Who has more London dispersion forces present? That would be glucose. Glucose has my winner with more London dispersion forces because it has more electrons. Now, does it have anything else to do with it? We're gonna find out briefly. Let's talk about which substances have a higher melting point. When we're talking about melting points, that gives us a piece of information. Use the test to take the test. Use the test to take the test. I need to move this again. Okay, there we go. So when I say a higher melting point, what I mean is I'm looking for who requires more energy to change. So if I have a high melting point, by default, I will have high intermolecular forces. So here's where we have to take that layered approach, that cumulative aspect, okay? So run with me. I'm looking at between these two molecules right here. Boron trifluoride and phosphorus trifluoride. All right. Boron trifluoride, I see a nonmetal. I see a nonmetal. I'm going to make that a little better for y'all. And a nonmetal, so I know I'm dealing with a covalent compound. And I see phosphorus here, which is a nonmetal, and fluorine's a nonmetal. I'm dealing with another covalent compound. So let's think, what things deal with covalent compounds? I got London dispersion forces, I have dipole-dipole moments, and I have hydrogen bonding. But the London dispersion forces is in all covalent bonds. Dipole-dipole things are only with polar things, like I see something's polar. So I know boron trifluoride has a special shape to it. I know that shape to be trigonal planar. But phosphorus trifluoride is a part of 5A, and 5A has that weird lone pair situation up top, pushing everything down. So I know I'm going to have a polar situation. So BF3 is non-polar. I'm going to say NP for short. And PF3 is polar. All right, so at minimum, I know BF3 has London dispersion forces because it's covalent. However, comma, PF3 here has London dispersion forces because it's covalent, and it has dipole-dipole moments. Particularly, what kind of dipole-dipole moments? Do we see any hydrogen bondings? I don't, because I don't see any hydrogens. So who would have a higher melting point? You can tell already. Who has more overall intermolecular forces? PF3. But now let's not discredit London dispersion forces, because a lot of a little makes an impact. Eventually, if you save in quarters and pennies and nickels and dimes, you will have a good sum of money here. So let's take into account our London dispersion force real quick. I have 1 boron, 3 fluorines. Boron is attributing 5 electrons. Fluorine is attributing 9. 1 times 5 is 5. 3 times 9 is what? I'll give you a second. Think about it. Think about it. And then over here, we got phosphorus with 1. There we go, phosphorus with 1. Phosphorus is contributing... Ooh, I lost it. Phosphorus is contributing 15 electrons over here. And fluorine is contributing 3 atoms of it. And fluorine is contributing that 9. Fluorine is contributing that 9. So 1 times 15 is 15. And 3 times 9 is, if we figured it out yet. And we're going to add that up. 27 plus 5. That's 32 electrons. And 15 plus 27. Let me get this going over here. That's 42. All right, so I'm looking at a 1 force. I'm looking at 1 force right here with 32 electrons, or I'm looking at 2 forces here, 1 force being 42 electrons, and a polar molecule. So overall, PF3 will have the higher melting point. Do the same thing for the other two. Do the same exact steps for the other two. So let's get to busy. I see phosphorus as a nonmetal. Hydrogen's a nonmetal on the metal side. And then we have nitrogen is a nonmetal. Hydrogen's a nonmetal. All right, I know phosphorus makes that funny shape. Pyramidal. And same thing with nitrogen over here. All right. So they're both polar. They're both covalent. So I know they are. Let me switch some colors here. I'm going to say covalent and covalent. They are both polar. So that's pretty much the same so far. So if they're both polar, that doesn't help me distinguish anything very much, because I know based on intermolecular forces, because they are covalent, they experience London dispersion forces, each of them. And because they are polar, they experience dipole-dipole. I'm going to name it dip-dip for short. And what's special? I do see something special about this one. This one has a member of FON attached to it. And I see hydrogens. So if I see a member of FON with hydrogens, I can expect some hydrogen bonding. All right, so, but let's not knock the little guy here. The London dispersion force calculations, I see 1 phosphorus. As I erase things. I see 1 phosphorus. And how many hydrogens? 3. And phosphorus is contributing that 9 we see. And hydrogen is experiencing that 1. 3 times 1 is 3. And 9 times 1 is 9. Overall is a 12 electron contribution for phosphorus trihydride and ammonium trihydride, or nitrogen trihydride, or ammonia, excuse me. That London dispersion force calculation, I see 1 nitrogen contributing 7 electrons, and I see 3 hydrogens contributing 1 electron. 7 times 1 is 7, 3 times 1 is 3, 7, 8, 9, 10. That'd be 10 electrons of an LDF. All right, now let's assess. I see both of them are polar, so they're both experiencing London dispersion forces and dipole-dipole moments. However, only one species here has a hydrogen bond effect to it. So we know those hydrogen bonds do not like to get separated because they're intensely bonded to their partner. So NH3 will have a higher melting point than pH3. What we're going over is evidences to support your claim. And the reasoning, the logic I'm giving you, comparing them, is your reasoning. The logic I'm giving is the reasoning. So you're looking at the greater cumulative effect. The greater cumulative effect. Now, let's talk about addressing the sodium chloride over here and this water molecule. Sodium chloride, I'm seeing a metal plus a non-metal here. And this metal plus a non-metal here, and then I see a covalent structure here with water, with hydrogen, it's a non-metal, and oxygen is a non-metal. So In the event I have a metal plus a non-metal, that is ionic. And we know water is covalent. Anytime you see ionic anything, ionic wins. So who has the higher melting point would be, traded over here, this sodium chloride over here. Because anytime you see anything ionic bonds are some of the strongest bonds we can make comparative to whatever London dispersion forces. Let me trade back to my pen over here. My London dispersion forces, my hydrogen bondings, and we know water is polar, so it's going to have some kind of dipole-dipole or dipole-dipole interaction. Even though water experiences all three of those, sodium chloride is ionic. It donates its electrons, making a very intense electrostatic attraction, so therefore, it has the highest boiling point. I hope that was helpful, guys. If you have any more questions, send me an email. This is the breakdown of intermolecular forces. Questions, send me an inbox.